Okay, so real quick, quick and close. I'm gonna have to kind of hustle with this, but I feel like I can, you guys. So, real quick, in math, one of the real purposes that math serves for us is that it provides models for making predictions and understanding things. Right? Like my background's in physics, and that's really all physics does. Physics is about understanding the way the world works. You know, understanding how gravity works and how forces interact and how electricity and magnetism work. Just everything, right? It relies almost completely on math to do that. What we have is if you study physics, you just see lots and lots and lots of equations, right, that make these predictions for you. So sometimes though math is asked to do stuff that's kind of hard to do. Like for example, what if we wanted to describe a situation where we want to model a person's altitude above the ground when they go skydiving. Say they're going to jump out of a stationary helicopter, really, really high altitude, to go skydiving. Okay? Describe that journey to the ground. Hopefully. It should look. What's it look like? Jump out of the helicopter, you step out of the helicopter, and initially your speed is 0, right? But then what happens? Say it again. Your speed rises, okay, right. You're accelerating, aren't you? So your speed's increasing. As your height diminishes, your speed's increasing, right? So your height is going to be changing in a way that's going to be increasing the rate at which your height is approaching the ground, right? Your speed starts off increasing. Does it increase forever? What eventually happens? Okay, it peaks when you hit what?
Terminal velocity.
Terminal velocity. Okay, so you get a point where the air that's rushing upward pushes on you hard enough to offset your weight, and you'll just fall at terminal velocity at constant speed for a while. Until you do that, then what happens? You pull the chute. And the chute unfurls, and you're going to be jerked up pretty hard, right? Because it's going to slow you down in a hurry. You're going to decelerate pretty rapidly when that parachute kicks in. Once you decelerate, then you're going to fall again with the terminal velocity, but a much lower terminal velocity because of the parachute. You just float down with the parachute, right? You just have so much more wind resistance, air resistance. Make sense? Okay, there were 4 distinctly different things going on in that story, though, right? Now, there are equations to represent each one of those, but each equation is very different. There's not a single equation that's going to take care of all parts of that journey to the ground, right? So how do you do that in math? Because probably if we were trying to come up with an equation, the input would be something like the time. Say we're going to start a stopwatch when you first step out of the helicopter, and the output is going to be maybe your height above the ground, okay? So I'm inputting times and it's outputting altitudes. But along the way, we've got to sort of shift gears a number of times because there's 4 different kinds of equations that we're going to have to leverage to do that, right? Because there's 4 different kinds of things going on. There is a way to deal with this in math. It's called a piecewise function. For this purpose, it's this purpose exactly. Very well suited. All a piecewise function is 2 or more functions, or we might even call them pieces, each with its own domain. Okay, what's a domain again? Okay, the set of x values, or the input values, right? All of the values we can input into a function, taken together, that set is called the domain. What do we call the set of all the output values from a function? The range, okay, good. All right, so then, now look closely at this. Here's an example of a piecewise function that has 2 pieces. It looks a little odd, like notice over here, it always ends up looking kind of like this. F of x equals, and then there's going to be this open script bracket. And that's just meant to tell us, that's the way that we're communicating that, okay, this is going to be a piecewise function. It's going to have more than one different functions combined at the same time. More than one piece is put together here, right? Now notice that there's 2 rows here. each one of these rows corresponds to a piece of the piecewise function. So the top one, the top piece is f of x is equal to the function x squared minus 1 if x is less than negative 2, right? So there's two things it's giving us. It's giving us the actual formula, or the rule that we're going to apply when we plug in values of x, and it tells us what are the values of x that work with that rule, with that piece, right? So there's really, I could kind of divide this up into two separate parts, right? I've got the first part of the piecewise, of each piece of the piecewise function is the equation, and the second part is the domain that goes with it, okay? So we could call this the blue function, and its blue domain, okay? Now, the other one, just so we can color code this, that's going to be the other piece. The other piece of the function is 5x plus 3, which is what we get when x is greater than or equal to negative 2. All right? So let's evaluate these functions then. What about the part A, f of negative 5? When I evaluate a function, I'm just plugging that value in for x, right? But which piece does that get plugged into, the top or the bottom piece? And where you have to look is in the domain. If I'm plugging in a value negative 5, where does that fit? Does that fit into the domain of values of x that are less than negative 2, or the domain of values that are greater than or equal to negative 2? Less than, right? Would everybody agree negative 5 is less than negative 2? Okay, so then this is going to be a blue function issue, isn't it? Right, so f of negative 5, we're going to use the top formula. So where I used to have an x, I'm going to plug in negative 5. What's negative 5 squared? 25 minus 1? 24. Okay, so then we know that f of negative 5 is 24. Okay? What about part B? We're going to evaluate the function at negative 2. Well, which piece do I plug negative 2 into, the top or the bottom? Top again, right? Because look, are you sure? How come bottom? Oh, okay, good. Yeah, it'd actually be bottom, wouldn't it? Because on the bottom piece is the one that we use when x is greater than or equal to negative 2. And in this case, we're plugging in a value negative 2. Right? So that's got to be a red function issue then. F of negative 2, we're going to use the bottom rule. So I've got 5 times the input plus 3, and the input is a negative 2. Okay? Well, that's just negative 10 plus 3 is what? Good. Okay? And then what about over here? 7. Top or bottom for me? Bottom. 7's greater than negative 2, isn't it? Right? So we do f of 7 equals 5 times the input 7 plus 3, so what is that? 35 plus 3 is 38. Everybody agree? Okay. Here's another example. How many pieces does this function have? 3. So 3 different behaviors for this function, 3 different rules depending on what the input is, right? Okay, so let's try graphing one of these things then, right? If we're going to graph one of these things, how many pieces in this piecewise function that we're graphing? 2, okay? When am I going to use the rule y equals negative 3x minus 7? Whenever what? Less than negative 1. When do I use the other rule, y equals negative 5? Greater than or equal to negative 1. So then, what's the important x value where we make the transition from between the two pieces? Negative 1. Agreed? Negative 1 is where we shift from one to the other. So what I'm first going to do, just so it makes it easier for me to deal with this, I'm going to put a line up here at x equals negative 1. Right? And that line is just y, or x equals negative 1, isn't it? That's the boundary between the two regions. Let's color code this, and I think it really helps. And when you're doing this This first assignment that we're doing from Unit 3, it's a paper assignment. There is no Moodle part of this at all. I think it's going to be helpful on this one to actually graph it on paper, right? And I think it's helpful to use like colored pens or pencils. I really do. I think just try to do it the same way I'm doing it here, and I think you'll understand it better. So let's make this our blue piece. Okay, and that's going to be when x is less than -1. So is that going to be to the left or the right of the boundary? To the left. Okay, good. So to the left, we've got the region here, and I'm going to go ahead and color code this. We've got this region to the left. Let's color the lines. There, that's much better. So there's the blue region, right? There's the region to the left of my boundary where we're using the equation y equals -3x minus 7. Okay? Let's make this our red piece. And so the red region is going to be where x is greater than or equal to -1, right? And so that one's going to be over here. Everybody agree? Okay, so everything to the right of my boundary is where we're graphing the line y equals -5. Okay, so all I've got to do here in a piecewise function is I'm going to graph the blue equation in the blue domain, and I'm going to graph the red equation in the red domain. And that's it. Okay? So let's do that process. How would I graph the blue line? Okay, so I could start at -7 on the y-axis, right? Because if I look at this, I've got a value of m that's -3, and b, the y-intercept, is at -7, correct? So we'd go down on the or the y-axis, we'd go down to -7, so 1, 2, 3, 4, 5, 6, 7. And then how do I use my slope triangle to graph another point? Normally I'd have -3 over 1, so I'd go down 3 and over 1. That's not very convenient for me on this piece of graph paper though, so. Okay, good, I could reverse it and just go up 3 and left 1 and get a point there. And then it only takes 2 points to graph a line, correct? Okay, so if I weren't worrying about the piecewise function, if I were just graphing the line y equals -3x minus 7 on the entire xy plane, I would just go like this, wouldn't I? I would just, there's my line. Except that's not what I'm doing here, is it? I'm only graphing the blue equation in the blue domain. So there's kind of a really light version of my line, but when can I actually put my pen down and make my blue graph? When I hit it, right? So I can only actually put my pen down when I get to the blue domain, and then I can put my pen down and make the blue part of the graph. But now what about the endpoint? I have to pay close attention to the endpoint. Am I going to include that endpoint or not? You're right, how come? It's not equal to. So the blue domain is only the values less than -1. So what kind of an endpoint should I put there? Open, right? Everybody agree? So I'm not actually including that endpoint. Okay, so now what about the red graph? The graph of the line y equals -5. What's that one look like? So I go down to -5, and then horizontal or vertical? Horizontal, yeah, good. So the y values are all -5. So there's my horizontal line. But once again, I can only actually put my pen down and draw that line in the red domain. So if I'm going from -infinity all the way up to +infinity, I don't put my pen down until I get to -1, x equals -1. And then I put my pen down, and it goes forever to the right. Now, what kind of endpoint do I have there? Closed, because I'm actually including -1 in the red domain, right? Okay, good. So that's what my graph looks like. Everybody see that? Got a blue piece and a red piece. And notice that they never overlap, right? It's a function. It never violates the vertical line test. The red solid endpoint overlaps with the open blue endpoint. Okay? What's the domain of the entire piecewise function then, though? Does it ever skip any x values? What do you think? It doesn't. You're right, it doesn't. In other words, if an ant were walking along this infinite piecewise function, when would he be walking on the blue piece? Well, he'd be walking clear from negative infinity all the way up to -1. He's on the blue graph, right? But as soon as he gets to x equals -1, he falls off the blue graph and lands on the red graph, right? But then from that point forward, he walks forever in the positive direction on the red graph. So he's got some place to step always, doesn't he? Right? So in other words, the domain is all reals. Okay? Now what about the range? The range, remember, is just that's just going to be, one way to think about that is, it's the projection of this whole thing onto the y-axis. Right? So let me make a copy of this whole page, and let's do this process. What's that? Yeah, this will be, I'm making a video of this right now. Yeah, so this will be, it's linked to, it's on my educational YouTube channel, but it's, you can get to it through Moodle. There's a link to it, right? Okay, so now what if we were gonna just project this whole thing onto the y-axis? So what would be the projection of the blue graph? If I were to squeeze it onto the y-axis, where would the bottom of that interval be? At y equals, what, like -4? Everybody agree? So that one's going to get squeezed over to here, and I get an open endpoint at -4. And then all these points up here would just squeeze over, and it would go up forever on the y-axis, wouldn't it? Everybody agree? So that part of the domain is just everything greater than -4. Well, what about the entire red graph? If I project that onto the y-axis, how many y values does it represent? I mean, if I squeeze that onto the y-axis, it doesn't cover very much of the y-axis. It only covers one point, doesn't it? All these points on the red graph only have one y-coordinate, and that's -5. So that entire thing just looks like a dot at -5, right? So then what's my range going to be? The blue part corresponded to y is greater than -4, right? What about, there's or, the red part? Well, the red part was one value. Y equals what? -5. So there's my range. Somebody agree? Okay. All right, one more thing though. So when we graphed the blue line, we created 2 points to create the line, right? But we only need 2 points to graph a line. Those 2 points in this case weren't in the blue region though, right? It wasn't such a big deal because they were very close to the blue region, but it may not be convenient for us to always do it that way, to use the slope-intercept use the y-intercept and the slope to graph a line. It may be that the y-intercept is way off the graph, or perhaps the boundary that forms the edge of your region is a long ways away from the y-axis, and then it's not very convenient to do that. So we might want to instead sometime just pick 2 points that are actually in the region that where we're graphing that piece of the piecewise function. In this case, the blue region, right? How could I do that? Do you remember back in Algebra 1, how did you go about doing that? When you wanted to generate some points to graph something, do you remember using a t-table? Did you ever learn about t-tables? If you didn't, that's okay. I'm going to show you now. A t-table just looks like a t, and then there's an x column and a y column, right? And I'm just going to, remember seeing this? I'm just going to input x values and then use my equation to calculate corresponding y values, right? Now, let's be really strategic about this though. If I want to create two really convenient points in the blue region, well, one of them will probably be the boundary between the regions, right? Because I want to know where the blue line is when it runs into the edge of the region. Agreed? Doesn't that make logical sense? So that's at x equals -1. So if I plug -1 into my function, what's -3 times -1? 3, okay, -7, -4. So you see that just gives me, it looks like an ordered pair, doesn't it, in the t-table? So I get the ordered pair -1, -4, which is exactly what we see here. If I go back 1 and down 4, well, there's that point, right? Let's pick another one. Well, how about if we pick one that's just a little ways away from that so we can space out our points just a little bit? What if I pick the point like -3? So if I plug -3 in for x to calculate y, what's -3 times -3? 9 minus 7, 2. Okay, so I'd go -3, +2. So 1, 2, 3, 1, 2. There would be another point. And I could have used those 2 points, which are actually in the blue region. See my point? Okay. All right, let's try one more of these. How about this one? It's got 3 pieces. Okay. So first of all, let's color code them. So we'll do blue piece, red piece, and green piece. How about? So what about the blue one? Where's the edge of the blue region going to be? Less than 0. Okay, so everything to the left of 0. The red is going to be between 0 and 6, and the green is going to be greater than 6, so to the right of 6. So I'm going to have 2 different boundaries this time, right? It's 0 and 6. Everybody agree? Okay. Okay. So there's one at 0. And there's one at, is that 6? I think that's 6, isn't it? Yeah. There's my 2 boundaries. The blue is going to be to the left of this boundary, right? So everything over here is the equation y equals what? -3x. Okay, and that's the blue region. Okay, the red region is going to be between the boundary lines. That's where y equals what? -1/2 x minus 1, good. And that's the red region, so we'll color that one red. And then the green region is everything to the right of the other boundary at x equals 6. And that's y equals x minus 7. Good. There's the green region, right? Okay. So all we got to do then is graph the blue function in the blue domain, the red function in the red domain, and the green function in the green domain. That's it. Okay, so let's start with the blue. Now let's go ahead and let's just make a t-table here. Let's just do this with a t-table instead of trying to use the y-intercept and the slope this time. So my blue t-table, what's one point that I should definitely include? Anyone want to suggest something here? Say it again. I could. That one's fine, but there's one I probably really do want to include. One of my 2. It only takes 2 points to graph a line, right? What should one of them be? If the edge of the interval is at 0, 0, right? Let's pick 0. So if x equals 0, what's -3 times 0? 0. Okay, so I get the point 0, 0. Is that going to be an open or a closed blue endpoint? Open, because the blue domain does not include 0. So the point 0, 0 is 1 point, and then we could do -3. If I plug -3 in, I'm going to get -3 times 3 is 9, which is a little off my graph, so maybe we'll pick something a little smaller. like -2, okay? So -2 times -3 is 6. Okay, so we'll go back 2 and up 3, 4, 5, 6. Okay, so we're done with the blue part. There it is. What about the red part? Let's make a red t-table. Okay, so I only need 2 points. Well, I have 2 boundaries in the red region, so why not just use the boundaries, right? And then just connect those to create the line in between. Do you have to do it that way? No, but it makes sense, doesn't it? So one boundary is at 0, right? And the other one is out here at 6. So we'll plug both of those values in to get ordered pairs. If I plug 0 into my equation, what do I get? -1/2 times 0 is 0, minus 1 is -1. So I get 0, -1. Right there. Is that going to be open or closed? Ah, closed. Look, because that one includes the equal sign, doesn't it? So we're going to get a closed endpoint at x equals, closed red endpoint at x equals 0. What about at 6? If I plug 6 in for x, what's -1/2 times 6? -3 minus 1. Okay, so we go over to 6 and down 4. 1, 2, 3, 4. Open or closed? Open. Okay, and then all I have to do is just connect those, because those are my 2 points that define the line, right? Okay, so there's the red piece. We're good? How about the green piece then? What's 1 point I definitely want to plug into the green portion? Okay, 6. So if I plug 6 in, 6 minus 7 is -1. So I get the point 6, -1. Open or closed? Open. Okay. And then I need one more. So how about like 7? If I plug 7 in for x, what do I get? 0. Okay, so I get 0.70. So right there, so there's the green piece of my piecewise function. Okay, make sense? Okay, now what about the domain? Look at that domain. And really, all we have to ask ourselves is, are there any pieces that we're missing? Let's see, if the ant walks all the way from -infinity, he's walking on the blue function until he gets to 0, and then even though he can't step on the blue function at 0, he can step on the red, so he's still got a place to stand. We walk along the red function until we get to 6, and then what happens?
Jumps.
There's no place to stand at 6, is there? He's got to jump over x equals 6, because there is no ground for him to stand on that function. There's no red ground and there's no green ground, right? But then once he goes above 6, he's fine. So what's the only value that's missing? 6. What do you think the easiest way to describe that domain is? I mean, one thing we could say is this. We could say x is less than 6 or x is greater than 6, and that's fine. But better than that, how about just saying x is not equal to 6? If I say x is not equal to 6, that implies that anything else is fine, but 6 is not, right? So there's our domain. X is not equal to 6. What about the range? What about the range? So if we were to squeeze all these parts together, what are the y values that are going to be graphed? Well, there is a bottom limit to all 3 parts, isn't there? Would you agree that's -4? So it has to be a value above -4. As we move up from -4, look what happens. Where the red graph stops, the green graph overlaps vertically, right? So we're okay there. There's no missing y values as we work our way up. We get up to -1, and then we're on the green graph. And look, the green graph overlaps with the blue graph. And so from all the way from -4 up to infinity, all those y values are graphed. Everybody agree with that? Okay. So if I were to squeeze all those parts over onto the y-axis, that would be the bottom, and it would just go up forever, right? So my range is y is greater than -4. Okay? Think you got this? Okay, good. All right. See if you can't get through about half of that worksheet tonight.